Hope all of you are doing great out there. I'd like to welcome each and every one of us to my discussion for today. And today we're going to look at an interesting concept of biological ligands for metal ions. And this is going to be assisting us in trying to identify various types of ligands which are going to be attached into metal ions. And as we said from our previous videos, this combination basically is going to be forming some of the most essential biomolecules that we're going to come across in our various physiological processes. Now, in a sense, this is going to be also assisting us in trying to, of course, try to see what are some of the conditions which are going to be, of course, used in trying to form some of the complexes. And we're going to be borrowing from our basic discussion, of course, of the combination of metals and non-metals, which is going to be involving some set of what we can refer to as ions or radicals. Now, in a sense, I'm going to be using this specific example, which we came across in our previous discussion on the concept of divination of particularly acids in our study of acids, bases, and salts. Now, we had said that if we have two chemical species of A, which is going to be an ion combining with B, to form, of course, a product which is going to be given in terms of AB. This is going to be resulting in the formation of what we refer to as a coordinate covalent bond, whereby we're going to see that one species, especially the A species, is going to be positively charged, and the species B is going to be negatively charged. And that has an implication that this specific species is going to consist of a number of electrons which are going to be particularly rich in electrons, while this one is going to be poor in electrons. And therefore, this specific combination is going to be joining for this specific electron and a positive charge to form this coordinate, of course, covalent bond. And this can be given in terms of the transfer of electrons, which we are going to see here. Now, in our previous discussions, we had said that basically for us to define what we refer to as an acid, we said that this is going to be a substance, or it can be defined as a substance that consists of hydrogen as the only positive ion. And in this particular case, this is going to be giving us a range of substances which are going to be consisting of hydrogen as the positive ion with a combination of other negative, of course, species which we're going to see given as such. So this is one of the ways in which we defined acids. And in a sense, we said that we can broaden this specific definition for us to find another way in which we can, of course, define an acid by using the Lewis definition. And therefore, we said that using the Lewis definition, we defined as what we refer to as a Lewis acid and a Lewis base. And in a sense, we're going to see that this is going to be different from the first discussion, or rather the first definition, which we have given hydrogen as a substance, which is going to be only positive ion in this specific case in terms of an ionic species. But for the Lewis definition of an acid and a base, we said that a chemical substance is going to be defined as a Lewis base if this is specific species, which is either in form of an atom, ion, and of course, or a molecule. So basically, this is going to be a chemical species which can be in form of an ion, atom, or a molecule that is going to be defined as an acid. And this is going to be that specific, of course, species that can accept a pair of electrons from what we refer to as a Lewis base. So therefore, we are going to see the concept of an electron being introduced in this specific case, whereby one species is going to be accepting an electron, whereby a pair of electrons, whereby the other one is going to be particularly giving out this specific pair of electrons. Now, in a sense, this is going to be resulting in the formation of such a kind of a bond which we have given above, which is going to be given as a coordinate. So this is going to be given as a coordinate covalent bond. And therefore, we can see that for this specific species to be defined in terms of an acid or a base according to the Lewis definition, we're going to have this specific substance that is going to be an electron donor, which is going to be given in terms of B. And this is going to be an electron acceptor. So the B is donating an electron to A, and therefore this is going to be given as an acceptor and a donor respectively to form this specific product. So therefore we can define A as an electron acceptor, a pair of electron acceptor, which can be defined in terms of a Lewis acid, and an electron donor, which is going to be given a definition of a Lewis base. Now, this is going to assist us try to define basically this specific concept of metals and ligands, which we can either refer to as a metal or ion, which is going to be defined as a Lewis acid, while the ligands are going to be referred to as a Lewis base. So therefore, from that specific approach, we can be in a position to identify various types of ligands and, of course, metal ions. And in a sense, we can have this one, therefore, given in terms of metal ions are going to form acidic parts or acids in this specific definition for biological ligands, whereby these specific ligands, so these ligands are going to be basically electron donors, while the metals are going to be electron acceptors. So therefore, from the previous definition of a Lewis acid base, we can define metals as Lewis acids, whereas we can define these specific ligands as Lewis bases. So therefore, the lower ones are going to be donating a pair of electrons to the metals in that specific formation of what we refer to as biological complexes. Now, in this specific case, the ligands are going to be referred to as complexing agents. And therefore, we're going to come across this specific term being used particularly for this specific aspect of ligands. Now, in this case, we are going to have a general example whereby these particular metals are going to be forming the complexes in conjunction with these ligands. And the function of the metal in this specific case is going to be forming the free ions and of course, which are going to be forming coordination or complex compounds. Now, this specific function of metals is going to be determined by the or defined by the geometries of the resulting compounds, which we have referred to as the complex or coordinate compounds. And these are going to be specifically biological, of course, complex compounds, which are going to be formed in this particular case that we're going to be using in our subsequent examples. So we have said about these specific functions of metals being, of course, determined by these geometries. And in coordination geometries, we're going to see that particularly for this specific set of ligands, which we're going to see, they're not going to be having regular shapes. And therefore, we are going to expect some kind of distortions which are going to be realized. And this, of course, is going to be defined or rather realized due to the environment of this or the shapes of these specific complexes, which are going to be irregular. Now, the metal ions are going to be forming centers in this specific case, whereby in case we have a general illustration for these specific complexes, we can have a metal ligand combination, which is going to be giving us various examples. So metals are going to be combining with a number of ligands. For instance, we can give this a specific of course, a combination which is going to be consisting of various ligands given as such. So this case where we are going to have L representing the donors or the ligands or complexing agents, and then we're going to have metals being represented by M. So the metals basically are going to be forming what we refer to as centers, and these are going to be coordination centers, which are going to be given in terms of these specific metals being surrounded by electron donors that we have referred to as ligands. So we can give different examples of ligands, which are going to be electron donors in this particular case. And these are going to constitute some of the elements which we have come across in our various discussions and the other forms of what we refer to as radicals. Now, in a sense, I'm going to be giving particular examples whereby we are going to have this specific element given in terms of examples of ligands. So we can give a few examples of this one, which include the element of nitrogen. And then we shall have other, of course, species, chemical species like the sulfide, the phosphate, and of course we're going to also have this specific, so we can have water as a ligand, which is given as such, and of course we're going to have oxides as ligands, and perhaps we can give these hydroxide ions as also another set of ligands which we're going to come across. So these are some of the examples which we can give in terms of these specific complexing agents which are going to be joined with metals to form complexes. And we're going to have three important ligands that we're going to be discussing in some of our subsequent videos, which are going to assist us basically understand the role of these specific biological ligands in biological systems or some of the physiological functions that we have mentioned in our previous video. So in a sense, we're going to have this specific ligands, so important ligands which we're going to come across, and in particular I'm just going to give 3 of them. So the first one is going to be proteins, or what we can give as peptides. So we have come across these specific terms, which protein is going to be a combination of amino acids, and therefore we're going to see that peptides as well is going to be amino acids which are going to be joined together from perhaps 2 species of amino acids, or rather 2 species, and these are going to be limited to numbers, of course, smaller than 100 units, and therefore these are going to be forming what we refer to as peptides, which is going to be forming an important ligand in our discussion. So we shall look as well at macrocyclic ligands. So from a study of the, of course, geometry, we so talked about aliphatic compounds and, of course, cyclic compounds. And in this case, we're going to have this specific previous use for macro, referring to as large, and therefore large cyclic ligands or molecules which we are going to come across. And this is going to be forming an important set of ligands which we are going to be discussing in our subsequent videos. And then lastly, we shall look at the examples of a nucleic or a nucleobases, which of course are going to be used, of course, which we're going to come across in our formation of the RNA and DNA given as such, which are nucleic acids given as such. So in this case, I've just drawn 2 specific illustrations on my right side of the board, and these are going to be one of the illustrations for the examples which I've given for, of course, this is specific, of course, ligands which we're going to come across. For instance, the first figure is going to constitute of what we call, of course, a macrocyclic ligand. Since this is going to be cyclic, and then it's going to be, of course, having a coordination center at this specific point. So I've, of course, intentionally put this specific coordination center just for illustration purposes. But if we are going to have potassium, of course, not being given in this specific case, the rest of this specific form of the structure is going to be giving us what we refer to as this specific macrocyclic ligands. And basically, this macrocyclic ligand is going to be given a name of a crown ether. So in this case, this is going to be a form of a crown ether. And we're going to come across various, of course, forms of crown ethers, which we're going to be, of course, discussing in subsequent videos. And this is going to be ranging from various sets of a combination, which we're going to see. For instance, for this one, this is going to be, of course, an 18 crown 6 given as such. So this is going to be 18 crown 6 given as such, and this is going to be a crown ether which we have been given that has got a coordination center of just potassium for illustration purposes. So in this case, basically this should have been given as such, but I've just given this one for the sake of illustration, since we are going to come across it in some of our videos. Now for the second state, we are going to have that specific figure, and this is going to be representing what we refer to as a porphyrin. And porphyrin is one of the examples of this specific, of course, proteins or peptides which I've mentioned. And we can give this one, or rather this is going to be also an example of what we refer to as the macrocyclic ligands. So the set of A and B, which I've given in the above examples, are going to constitute what we refer to as, of course, macrocyclic ligands. So for proteins, we shall look at a few examples of them from the 3 basic, of course, divisions of primary, secondary, and tertiary form of proteins. And this is going to be assisting us try to differentiate between the various range of proteins. But just given various examples of these specific proteins. And one of the examples, basically, which we had used in our previous video, consisted of this specific form of a protein which we had given in terms of cysteine. And this is going to be, of course, given as such. So this is one of the examples of amino acid, which is going to be, of course, forming a set of building units for proteins. And therefore, there are various range of other proteins which we are going to come across, or amino acids which we are going to come across, that are going to be forming building units of proteins. Now, in a sense, a combination of these specific two, for instance, is going to be forming what we refer to as a peptide. And for such a kind of a protein which is going to be given as cysteine, this is going to be joining through the thiolate, thiolate center, which I can give in this specific case. So for instance, if we had another similar molecule, then this is going to be joined to the other molecule using this specific center that's going to be given in terms of this coordination. So the rest of this specific molecule which is going to be given as such is going to be joined on the other side of this specific molecule. So we're going to have a similar molecule. So suppose this section of the molecules, we're going to have another section given as A, and this is going to be forming what we refer to as a disulfide bond. Now, for such a kind of a molecule like the cysteine molecule is going to be joined by a disulfide bond, and they're going to form another species which is going to be given a different name that we're going to come across. And basically that's going to be forming a set of what we can refer to as a peptide in this specific case. And lastly, perhaps we can look at just a difference between these specific two and some of the ligands which we're going to come across, basically which are going to be building blocks of the nucleic acids that we have given as one of the examples of important ligands that we're going to come across. So in this case, we're going to have these specific molecules for the dioxyribose and of course ribose nucleic acids, which is going to be formed by this specific, of course, set of section of the molecules. So I'm just going to have this one given in terms of this particular illustration. So for this one, we shall have this one given as such, and we're going to have this one given as such as well. So this one we're going to have a CH2 and OH given as such, and of course we shall have this one given with a, so perhaps I'm just going to give this one correctly. So we're going to have this one given in terms of this specific conformation, and then we shall have another one which is going to be given as well using. So I decided basically that this specific set of molecules are going to be of pentose class, and they are going to be given as ribose sugars whose specific structures can be given in terms of these specific cyclic forms. So we are going to have this one as well given as H, OH, and this one is going to be given this specific illustration given as such, and we're going to have this one given in terms of HCH2 OH given as such. Now, the difference between these specific two sets of blocks for building of this nucleic acid are going to be seen in this particular case, whereby we're going to have this one given as deoxyribose, and this is going to be a ribose sugar given as such. These are, as I've said, the two sets of pentose class, but there's a difference in their formation, whereby we're going to see that in this specific case for the deoxyribose, there's of course OH group. So basically this is going to be the opposite. So we shall have this specific OH group for the ribose sugar, which is going to differentiate it from the deoxyribose sugar that has got only H in terms of this is specific section for the molecule, especially for this carbon. So in our last discussion, we had talked about the concept of various range of sets of carbon, which we're going to come across in this specific case. And I'd mentioned the concept of a numeric carbon, which is going to be, of course, assisting us try to define these specific sugars which I've given as such. So in this case, this is going to assist us to differentiate between various ligands which we are going to come across for metal ions, and for the important ones which we have given, for instance, for the proteins and peptides, which are going to be a set of amino acids, and macrocyclic ligands, which constitute of the crown ethers and what we refer to as apophyrenes. So this is going to be an example of apophyrin molecule, which is one of the examples. The two are examples of macrocyclic, of course, what we refer to as macrocyclic ligands, and they're going to assist us in trying to form some of the important molecules which we have been as these apart from the of course, the ribose sugars, which I've shown above. So kindly check our description boxes for various links of other videos. Engage us in the comment section and also ring that notification bell for other updates on different discussions on various topics in math and the sciences. So in our next discussion, we're going to look at deeper examples of some of these specific ligands. And that is going to be forming our final set of the concept of bioligands and metals and some of their specific, of course, relevance in our biological system. So that is it for now, guys. Bye, God bless you. Catch us in our next video.